Today we explore one of the most remarkable discoveries in condensed matter physics, the quantum Hall effect, discovered by Klaus von Klitzing. At the heart of this discovery lies a two-dimensional electron system, subjected to extremely strong magnetic fields at very low temperatures. Before we understand the quantum Hall effect, we need to understand the classical Hall effect discovered by Edwin Hall in 1879. When electric current flows through a conductor in the presence of a magnetic field, a voltage develops perpendicular to both the current and the field. Here we see a conductor with current I flowing through it, magnetic field B perpendicular to the current, and the resulting Hall voltage developing across the width. The Hall resistance is defined as the Hall voltage divided by current, which equals B over N ET, where N is the carrier density, E is the electron charge, and T is the thickness. The classical theory predicts that Hall resistance should vary smoothly and linearly with the magnetic field strength. In 1980, Klaus von Klitzing performed a groundbreaking experiment using a silicon MOSFET device. The experimental conditions were absolutely crucial for observing the quantum Hall effect. First, extremely low temperatures were needed, typically below 4 Kelvin, often even below 1 Kelvin. Second, very strong magnetic fields were required, ranging from 10 to 20 Tesla. Third, and most importantly, the sample had to be exceptionally clean, forming a true two-dimensional electron gas. This diagram shows the MOSFET structure with a silicon substrate, an oxide layer, and at the interface, a two-dimensional electron gas where the quantum Hall effect occurs. What von Klitzing observed was completely unexpected and revolutionary. Instead of the expected smooth variation with magnetic field, the Hall resistance showed perfectly flat plateaus at specific values. This graph shows the quantized Hall resistance as a function of magnetic field, with perfectly flat plateaus and sharp transitions between them. The plateau values follow a simple formula. RH equals h over E squared times 1 over n, where h is Planck's constant and n is an integer. The integer n takes values 1, 2, 3, and higher integers, creating a series of quantized resistance values. Let's calculate the numerical value of this fundamental quantum. The von Klitzing constant is defined as Rk equals h over E squared. Planck's constant h equals 6.626 times 10 to the minus 34 joule seconds. The elementary charge E equals 1.602 times 10 to the minus 19 coulombs. Calculating, Rk equals 6.626 times 10 to the minus 34, divided by 1.602 times 10 to the minus 19 squared, which gives 25,812.807 ohms. Remarkably, this value has been measured to an accuracy better than 1 part in 10 billion, making it one of the most precisely known physical constants. Let's understand why classical and semiclassical models completely fail to explain these observations. Classical physics predicts that resistance should vary smoothly with sample impurities and disorder, but the observed resistance plateaus remain perfectly flat even in samples with significant disorder. Amazingly, both dirty and clean samples show exactly the same quantized Hall resistance values, a behavior impossible to explain classically. The exactness of the quantization is universal and completely independent of sample-specific details like geometry or impurity concentration. To understand the quantum Hall effect, we need to introduce Landau levels, the quantized energy states of electrons in a magnetic field. When electrons are confined to 2 dimensions and subjected to a strong perpendicular magnetic field, they can only occupy discrete energy levels called Landau levels. The energy of the nth Landau level is given by h bar omega c times n plus 1/2, where omega c is the cyclotron frequency. The cyclotron frequency omega c equals Eb over m star, where m star is the effective electron mass. This energy diagram shows the discrete Landau levels labeled by quantum number n, equally spaced in energy. Each Landau level has a finite degeneracy, meaning it can hold only a finite number of electrons. The key concept connecting Landau levels to the quantum Hall effect is the filling factor. The filling factor nu is defined as the ratio of electron density Ne to the density of available states Nb. The density of states per Landau level, is NB equals E B over H. When the filling factor equals an integer, exactly that many Landau levels are completely filled with electrons. Here we see a filling factor of 2, with the two lowest Landau levels completely filled and higher levels empty. At integer filling factors, there is a finite energy gap that must be overcome to add more electrons, which is the key to understanding the plateaus. Now let's address the central puzzle. Why are the plateaus so incredibly flat and precise? The question is, how can the Hall resistance be completely independent of disorder, impurities, and sample geometry? The answer lies in topological protection through edge states, a concept that was revolutionary. At the edges of the sample, special edge states form that carry current in one direction along each edge, bypassing all the disorder in the bulk. These edge states are topologically protected, meaning they cannot be scattered by impurities or defects. The mathematical explanation involves topological invariance, as shown by Thulis, Komoto, Nightingale, and Den Nies. The Hall conductivity sigma xy equals n times e squared over h, where n is a topological invariant. The integer n is not just any number, but a topological quantum number called the Chern number. The Chern number can be calculated as an integral over the Brillouin zone of a quantity f of k called the Berry curvature. Remarkably, this integral can only take integer values due to topological constraints, which is why the quantization is exact. Let's calculate the actual resistance values for the first few plateaus. The Hall resistance equals h over Ne squared, which is the von Klitzing constant divided by n. For n equals 1, the Hall resistance is 25,812.807 ohms. For n equals 2, the resistance is 12,906.404 ohms. For n equals 3, the resistance is 8,604.269 ohms. For n equals 4, the resistance is 6,453.202 ohms. These resistance values are absolutely universal, independent of the material, sample size, or temperature, as long as the quantum Hall regime is maintained. The extraordinary precision of the quantum Hall effect has had profound practical implications. Modern quantum Hall measurements can achieve precision better than 1 part in 10 billion. Since 1990, the quantum Hall effect has been used to define the International Resistance Standard. The quantum Hall resistance standard replaced older standards because of its exactness, reproducibility, and fundamental connection to universal constants. One of the most surprising aspects is the role of disorder in the quantum Hall effect. Here's a fascinating question. Does disorder help or hurt the quantum Hall effect? The paradoxical answer is that moderate disorder is actually necessary for observing sharp plateaus. Without disorder, there are no plateaus. With optimal disorder, we get sharp plateaus. With too much disorder, the effect is destroyed. Disorder localizes electron states in the bulk of the sample, which actually enhances the role of the extended edge states that carry current. The story doesn't end with the integer quantum Hall effect. In 1982, an even more exotic phenomenon was discovered. At even lower temperatures and higher magnetic fields, additional plateaus were observed at fractional values of the filling factor. Plateaus appear at fractional filling factors, like 1/3, 2/5, 3/7, 5/2, and many others. The Hall resistance formula still applies, but now nu can be a fraction. The fractional quantum Hall effect cannot be explained by single particle physics. It requires strong electron-electron interactions and creates exotic quasi-particles with fractional charge. The quantum Hall effect has profound connections to many areas of modern physics. The topological concepts introduced by the quantum Hall effect led directly to the discovery of topological insulators and ideas for topological quantum computing. The quantum Hall effect in graphene shows unusual behavior due to its special band structure, with plateaus at different filling factors. The quantum Hall effect sits at the center of a web connecting topology, graphene, topological insulators, fractional quantum Hall effect, anyons, and quantum computing. In 1985, Klaus von Klitzing was awarded the Nobel Prize in Physics for his discovery. Von Klitzing made his groundbreaking discovery on February 5, 1980, at 2 a.m. in his laboratory at the High Magnetic Field Laboratory in Grenoble, France. The Nobel Committee recognized both the fundamental theoretical importance and the practical metrological applications of the discovery. The Nobel Prize medal represents the highest recognition in physics, awarded to von Klitzing for opening an entirely new field of research. Let's summarize the key mathematical insights that explain the quantum Hall effect. First, Landau quantization creates discrete energy levels in a magnetic field. Second, the filling factor determines how many Landau levels are occupied. Third, the Hall conductivity is quantized in units of E squared over h. Fourth, the Chern number is a topological invariant that must be an integer. Fifth, edge states are topologically protected and carry dissipationless current. Let's discuss the experimental signatures that confirm the quantum Hall effect. The first signature is perfectly flat Hall resistance plateaus that persist over a range of magnetic fields. The second signature is that the longitudinal resistance simultaneously drops to essentially zero on the plateaus. The quantum Hall effect is a fascinating phenomenon that connects topology, quantum mechanics, and condensed matter physics. This discovery has led to a deeper understanding of quantum systems and their potential applications in fields like quantum computing and material science. The quantum Hall effect stands as a testament to human curiosity and the power of scientific inquiry to reveal the secrets of the natural world.